In a previous chapter of this version, we used the ability of Spectro-X to display multiple channels of data simultaneously, along with markers, to make a time difference measurement between channel 1 and channel 2. In this case, it was perhaps the time difference, or the transit time, between a pulse being transmitted and the channel reflected energy of that pulse being received in a second channel, and then measuring the time difference between the two. But we can also use Spectro-X to make frequency difference measurements as well, but we would obviously want to use the frequency domain plots as opposed to the time domain plots to help us visualize and place markers to correspondingly make those frequency difference measurements. In this case, we have two channels with linear chirps transmitted and received, but we note that as the transmissions progress, all of a sudden the transmitted pulse seems to have shifted in frequency. And the question is, how might one make a measurement that allows you to determine what that frequency shift was? The way to do that is to use the persistence spectrum and certain features of the persistence spectrum that are available to the user. You can change essentially the memory duration of the persistence spectrum, very similar to what used to be able to be adjusted as the phosphor level, or the phosphor brightness level or decay level in multi-channel oscilloscopes. Here we're going to go ahead and set it such that it does not ever forget, or that visual memory or that visual persistence is actually going to be infinite in length. And we're going to also turn on a max hold feature, which will help us to see what the upper frequency limit of the chirp is as it progresses from this lower frequency grouping, start and stop, to the upper frequency grouping of the shifted chirp from here to here. So with those turned on, I'm going to go ahead and replay this section of the recorded channel and pick up the two shifted pulses as well as the previous pulses. And with the max hold and infinite persistence in the playback persistence spectrum, it should be fairly easy for us to go ahead and look at those in substantial detail. So here we have the pulses prior to the frequency shifting taking place. And as this plays through, we can pause it and place a marker at the peak point of the unshifted chirp. And then allowing that to continue to play, we'll get to the point where the frequency shift takes over. And with the max hold feature, it will go ahead and display and hold the maximum frequency of the frequency shifted chirp. So we'll go ahead and place a second marker at that point, go back to our marker math window, and ask it to perform a difference measurement between marker 4 in red and marker 5 in green. And notice that what we found, even though we were placing the markers in the persistence spectrum, because the markers are correlated across windows with matching measurement domains, in this case frequency, they'll show up in the other windows that also display frequency related information. So here was marker 4 placed at the maximum duration of the highest power level of that chirp. And here, as you can see, because of the color index indicating power in the spectrogram, here is that marker correspondingly placed in the playback scrolling spectrogram, and the green marker for the shifted pulse showing up at essentially the same point in the shifted chirp in the playback scrolling spectrogram. But these are only going to give me a relative indication that in fact I have properly placed the marker. The key question is, again, can we determine quantitatively what that shift was? So if we go to the math function, designate marker 5 and marker 4 as the parameters to go into that difference measurement and compute that difference measurement, we see that the delta frequency, or the frequency shift in this case, was a little bit more than 5 megahertz, 5.0825 megahertz in frequency shift. Similarly, as we saw earlier in chapters, in the time domain plot, we can go ahead and place markers, in this case, not only within individual channels, but we can place markers in multiple channels. And if I wanted to make difference measurements between any of the two markers, whether they're in the same channel or in different channels, and again, as we saw previously, move those markers anywhere that we want so that we can make difference measurements very easily and compare one set of markers to another.